Okay, so sound is measured in decibels for loudness, just like it's measured in hertz for frequency. And we say, hey, you know, this might have a lot more decibels than another thing. Okay, so you think that a purring cat has 25 decibels worth of energy in its sound. That's how loud it is, right? So an average home might be 50, a vacuum cleaner would be 75, and it would lead you to believe that a vacuum cleaner is 75. Okay, so it's 3 times greater in sound than a purring cat. But that's not even close to what it really is. That's where this decibel unit is kind of weird. So uh, if we were counting by like one at a time, and that one meant one, that would be normal, right? 25 to 75, you'd have 3 times as much sound in it. But since sound is kind of weird, the more energy you get, it doesn't just make it sound that much louder. Um, it's partly just because of how much energy can be compressed into a wave. But so imagine for a second that um, every one step on here represented 10. That's what we would call a log scale. So going from 25 to 26 wouldn't represent really 1 over 25% more energy being compressed as sound. It would actually represent 10 times more than the thing before it. So in log scales, basically every time you're moving up, it goes up by 10. So if you're going up 10 on a log scale for decibels, it would represent 10 times 10. And if you're going up another one, you go by another 10. So instead of 25 to 75 being 3 times greater, it's actually something closer to, let's see, so it would be 10,000 times greater. Is every time you go up 10 on a decibel scale, you're actually changing by a factor of 10. It's so weird, I know. So in other words, if something on this scale, let's just pick an easy one, right? Rustling leaves compared to an average sound of a home, the amount of energy in the sound of the home, it wouldn't be like 30 more sound. It's 20 to 30, which would be 10 times more, and then 30 to 40, which would be another 10 times more, so 100 times more, and then 40 to 50, which would be another 10 times more. So in other words, an average home has not just 30 more sound, it has comparatively 1,000 times more energy in it than rustling leaves does. That doesn't seem like such a big deal, but once you start thinking about times 10 times 10 times 10, going all the way up to 80, now it's a million times. A noisy restaurant might be a million times more energetic than rustling leaves in terms of the energy that goes into it. So humans, we might be able to hear pitches between 20 hertz and 20,000 hertz. The pitch doesn't hurt us. Sometimes pitch can make humans feel funny. If it's below 20 hertz in the teens, it kind of makes us feel weird. It can make us angry or scared, but it doesn't necessarily hurt us, right? Because even though it's high frequency, it also has to pack the punch of the amplitude or the volume with it. So the pain threshold for hearing is about 120 decibels. That's our body's indicator, our ear's indicator that's saying, hey, this is a lot of sound right now, right? And just to put that back into scale, 120 decibels is pretty dang loud. You think about like a lawnmower being 110 decibels, a chainsaw being 115. Rock concert might be a little bit louder than this, right? That's where you're physically going to feel pain. That's an indicator that your ears are getting damaged actively. And if you're sitting next to a jet plane taking off, you would probably go deaf almost immediately because there's so much energy. Remember, even past where you feel pain, that'll be another 10, 100, 1,000 times more energy from what would feel painful to where a jet engine is taking off. So that's why this is actually a more helpful scale. When you're talking about things that have big changes over time, and you want to make them more meaningfully compressed, that's where we use logarithmic scales. You're going to have fun with that someday in math class, but I am not going to dig into it any more than that. Let's just take a look at some of the loudest noises there are. So concert speakers might be 135 to 145 decibels. That's a good 10 times louder than, or 10 times more energy than would be not painful for you. So you're like, why not go to a concert and stuff something in your ears? Well, just be smart about it. Musicians that play these concerts and they don't have ear protection would go deaf after a couple years, right? Where they lose the ability to hear themselves sing or play the way they'd like to. There's no shame in going to a concert that's loud. I know it's fun, but just wear some ear protection first. That way you can continue to go to concerts by the time you're 70. Fireworks are much louder, and of course everything here is just depending on how close you are to something. Gunfire might be 150 to 155 decibels. And there's also how long you're sustaining that amount of energy in your ears for, right? A short amount of time is much better than even a lower amount of energy and a longer amount of time. So something like the space shuttle, 165 to 170 decibels. Literally, if you were next to a space shuttle, you would die just from the sound. And remember, sound represents the amount of pressure that matter goes under. So space shuttles, the rockets on those, the space shuttles would compress so much energy and pressurize so much air that it would literally like rip your cells apart as it goes through you. So you would die from that. Even the astronauts in the space shuttle would die. So they developed a really, really impressive system for taking out the energy from the sound underneath. They shoot a lot of water into it to make sure that the energy goes somewhere. So instead of into shaking things, the energy goes into transforming the water into steam. Ridiculously, a blue whale, if like a point-blank blue whale call, is actually much louder than that, which is just insane to me. And I don't even understand how something makes that much energy into its sound. Blue whales can communicate over really, really long distances, right? So hundreds of miles underwater, also they have low pitches and high pitches. Some whales have really nice sounds, right? But lower pitches will travel further without ending up interacting with stuff along the way. Then you have like cataclysmic events like volcanoes going off, huge bombs, huge earthquakes, which we talked about how much energy is in those things before, right? To give you an idea, remember every 10 you go up in here represents another 10 times as much energy. And then you have things like meteors exploding. So, something like this, it seems like, wow, it would be so loud. But, the further away you get, the very, very quickly the sound of it goes down. Otherwise, we'd be hearing blue whales all the time, right? Another blue whale is coming by New York right now. It's like we'd be able to hear it. But the energy dissipates quickly because it's spreading out like butter on toast. I'm going to skip over this example, but if you want to take a look, you can try and figure this out, and I'm going to tell you the answer in just a second. Okay, so to figure this out, hopefully you use the logarithmic scale here. Going from 140 decibels, which will be a concert speaker, to 180, that's a total change of 40, right? So on here, the power would change from, say we go from 10 to 40, or 140 to 180 is the same thing, right? So 40 to 80, even if you're thinking about it like that, you'd have 10, and that will get us around here. So it would be 1,000 times greater. 10 times 10 times 10 times 10 more energy in that blue whale call than you'd have in a blaring concert speaker. I actually think it would be 10,000 times greater. So let's think about how sound travels through different states of matter. This is a picture of me doing something very stupid, and I wouldn't recommend it. However, if you know Fox Chase, this is actually on the other side of the tracks from where the big stoppage is. There's an old story that cowboys used to listen to the rails for trains before letting their cattle pass over, because you could actually hear the train through the steel from much farther away than if you were able to see it. And if cattle take a long time to get from one side of the tracks to the other, they wanted to make sure that they were safe. But yeah, sound definitely travels faster through solids than it does through liquids, and much faster through liquids than it does in gases. So don't tap on a fish tank. Don't be like that, because it travels much faster through a liquid than it does through gas. And if you've ever seen the Darla scene, where very famously she's tapping away, that's absolutely how fish might feel. Because if you're compressing a lot more of this matter, that matter is going to quickly pass along that signal to whatever it's feeling, whatever is actually receiving that signal. To put in perspective here, I know this is in the video from before, but if sound travels at about 300 to 343 meters per second in air, depending on how much, like how dense the air is, how much humidity there is in the air, it travels 6,000 meters per second in steel. Much faster. Light travels even faster than that. I think it travels closer to like 300,000 meters per second in a vacuum, but that's in air. So we'll just skip through these examples because we're getting kind of low on time here. The reason that it travels faster through a solid is just because it's easier for that energy to be passing between those molecules. They're more tightly packed together. If this is going to hit this, it takes less time for this to hit this than it does for this one to travel all the way over here to hit this one, to travel to this one. You get the idea? And because, once again, there's no actual molecules in space, it's like the least dense gas you could have. There is no sound. So if you were to think about speed now, think about how do you go faster than sound? What does it mean? If pitch and frequency are related to each other, and we measure them in hertz, and loudness and amplitude are related to each other, and we measure them in decibels, what can we do to measure the speed of a wave? So real quick, I'm going to talk about this as an example just to make sure we're on the same page here, right? You have these 4 different examples. I want you to go ahead and think about which one represents a high loud pitch, a high low pitch, a high soft pitch, a low soft pitch, and a low loud pitch. Gosh, it's a tongue twister. Take a second, pause your video, and also work on this in your guided notes. Okay, here are your answers. Pause away, take a look at it, but we're running out of time here, so I'm going to keep going. The Doppler effect is this idea where if you were to hear a car coming by, and I think you're not going to be able to hear, yes, you're not going to be able to hear this, but if you were to go onto the slides, you should be able to click into that. You ever hear an ice cream truck coming? It makes it sound like it's higher pitched when it's coming towards you than it does when it's going away from you. And this change in frequency as sound gets closer to you is what we call the Doppler effect. It's not that the frequency is actually changing, it's just that it appears to change as it gets closer to you. So if we're thinking here, the closer a sound gets, the higher the pitch seems to be, and the farther away a sound gets, the lower the pitch seems to be. And it's not necessarily just how far and how close it is, it's whether it's traveling towards us or traveling away from us. Once again, you can click on that video online to take a look. So when we think about this, it's also kind of related to the Doppler effect, is also related to light as well. We talked about this when we talked about universal expansion and the Big Bang Theory, of how light will actually look like it's a different color. So spoiler alert there, if frequency sounds like pitch to us for sound, frequency looks like color for us for light. And if amplitude sounds like a louder noise to us for sound, then it looks like a brighter light for light. Okay, so don't forget to fill out your exit ticket for lesson 2. Go ahead and do that now before you're done here, and I'll see you for lesson 3